All right, let's discuss a topic of rotational inertia of solid objects. And you probably have seen the different forms. So if you have, say, a solid sphere or a hoop or some object that's not point masses, and you'll see these values, they have mr squared or 2/5 mr squared or 1/12 ml squared for the moment of inertia of a rod. The question is, where do these things come from? So we're going to talk about the rotational inertia of solid objects, continuous objects, not point masses. We're going to see where they come from. So this does involve a little bit of calculus, but it's a little bit tricky because the calculus is in multiple dimensions. So the form that we're going to use for the rotational inertia of a solid object is given by an integral. We're going to use the adding ability of an integral. It's going to say that we're going to look at how far are we from the axis of rotation to each individual little piece of mass. So it looks very similar to sigma m r squared, right? We look at the case where we add up all of our little masses, each little point mass to it. The way we do this with calculus is we convert it into an integral. So we look at some small infinitesimal section of mass. We figure out where that infinitesimally small section of mass is, and we add it all up. So really, all we're doing is we're looking at each individual little moment of inertia, so each atom, and we're going to add up each atom to give us our moment of inertia. Well, there's one problem with this, and the hard part for this, conceptually, this is easy. The hard part is figuring out what dm is. We have a radius squared, so in order for us to complete this integral, we have to somehow relate how does the mass change if we're at different radiuses. So if I have an object, some weird shaped three-dimensional object, right? Looks something like this. I need to figure out where is my little dm and its radius out. And I'm going to then figure out how do I go through and add up all my little dm's. For a shape like this, it's going to be very difficult. But we can use our idea of calculus with some of our shapes, some of our standard shapes, like a sphere, or a rod, or a disc, hoop. All of these are nice symmetric shapes, right? They look like we have, from an axis of rotation, we can say, hey, look, we know how these points are, where they are. We can actually describe this using math. With a rod, it's actually really easy. We put a rod here, and we go, hey, look, we have mass to the left, we have mass to the right. We know how to look at some small little section of mass here and add it up to everything else. Hoops are really nice. We have a hoop that looks through. We see that all of our mass is at one radius. So we look at one little section of mass here, and we figure out how it changes around. So this is the full form of rotational or moment of inertia for solid objects or continuous objects. So when we come up with these, when we actually solve these equations out or solve these shapes using this equation, we will find where we get these coefficients, where we get like the 2/5 mr squared from. Where does that 2/5 come from? Why is it different from the 1/12 ml squared in this case? Or why is the disk a 1/2 ml squared and the hoop is mr squared and the hoop is mr squared? So why do these shapes show up? Well, it's coming from us completing this integral. So this is just the basic concepts of what the moment of inertia looks like for continuous shapes. So sometimes you're asked to solve problems like this. You may or you may not be, but this is the general theory behind how these moments of inertia are produced.